Okay, so let's look at the readout process in more details. So we described what will happen if you read out 1. So let's look at the waveform from this timing diagram. So initially, your bit line will be precharged to be half VDD. So this is your bit line. And then in this case, we read out 1, so your storage node will be VDD. Now we turn on the word line here at this moment. This blue curve is the word line. So we turn on the word line. And typically, word line will be boosted up to a higher value called VPP, which is higher than the VDD in the practical circuit. But anyway, the word line is turned on to some positive high voltage. So it's like this transistor is turned on. So then after that, you will see that here the voltage on the bit line will increase, as we said. To read out 1, then bit line voltage will increase by delta V. So you see here this voltage will increase. At the same time, the storage node voltage will decrease. And eventually, those two voltage will be the same. So why is that? We are going to analyze this through the simple circuit, like those two capacitors on this diagram. But let's mark this. This is the delta V we are talking about. This is the voltage increase on the bit line. So let's look at this circuit. We have two capacitors, right? So this is your storage node, and it has this Vs voltage. Storage node attached to this cell capacitor, Cs. And this is your transistor, 1T1C. And the other side is the bit line. And bit line has this parasitic capacitance, CBL. So this circuit is a charge sharing circuit. Why is that? Let's look at before you turn on the word line, what do you have? Before you turn on the word line, that means this transistor here is off. So it's like open circuit. So here is like a switch. You open circuit, this switch. So there's nothing here. So those two sides are isolated. But we can look at the total charge we have on those two capacitors. So on the left-hand side, on the DRAM cell, so what is the charge stored on this capacitor? So you know the charge is the voltage across this capacitor multiplied by the capacitance. And on the Q cell, you will have Cs times VDD. On the other side, this CQBL on the bit line, what is the voltage? So on the bit line, the voltage is initially we precharge to be half VDD, and then you have this CBL. So the charge on the bit line will be CBL times half VDD. So here I got one question: what is the SN? SN is the storage node. Here, this node. So SN is the storage node attached to the capacitor. And here, in this example, we assume it stores 1, so it's VDD. So you have the total charge on those two sides. It's like this. Another question in the graph: what is VBB and VSS? Okay, so that is just low level. So this is like your ground. Like your ground. This is your VDD. And this VBBW, so for the word line, it will be even biased to some negative voltage in the real circuit, but we are not going to discuss that. So for the word line, the low level and high level is different from the bit line's high level and low level here. So the word line is, the low level of the word line is biased to negative voltage. This is to reduce that off current through the transistor. We are going to discuss that later when we discuss the retention of the DRAM cell. We want to minimize the off-state current, so we bias the VLAN to be a negative voltage. Okay, so basically, and this is the low level for the VLAN and high level for the VLAN. And let's go back to this circuit. Before you turn on the transistor, then you have those total charge on the left hand side of the equation. So this is initial charge. And after you turn on the VLAN, so this transistor is on. That means you close this switch because the current can flow through the transistor. So in this case, this current is flowing to the right because this is VDD, the other side is half VDD. So we are going to discharge the CS, but going to charge the CBL. Or in other words, you are going to share the charge between those two nodes, or you take the sum of the charge from the VS to the VBL. Eventually, the VS and the VBL will be equal potential. Then the charge sharing process will stop because they are equal potential. There's no current flow eventually. So eventually, those two nodes will become one node with the final voltage, let's say the VBL new. This is the new voltage of the VBL, which will be the same as this VS, which is this voltage here. This is the VBL new, this node. And you can solve for this VBL new. So you just move the CS plus CB to the left-hand side. You can solve for the VBL new. In this process, you can have this equation because the charge is conservative, right? Charge will not be lost. So you can have this equation before and after you turn on the VLAN. So you can solve for the VBL new. And then that will be this voltage, VBL new. So you can solve for this VBL new. And then you can minus this VBL new with this initial VBL, which is half VDD. So you use this VBL new minus the initial VBL. Basically, you are going to use this point minus this point. You will get the delta V, the difference. So you can calculate that. I will skip the derivation, but it's just some matter of math. You just move the terms around, and then eventually you can get this equation for the delta V. So that is a change of the bit number voltage. So it's 1 over 1 plus CBL over CS. Let's use CBL for the bit and capacitance. So CBL over CS and multiply by half VDD. So this is the delta V. So why do we care about this delta V? This is called the sense margin. You rely on this sense margin to determine the output. And as we discussed in the previous slide here, if you read 1, this delta V will be positive. If you read 0, this delta V will be negative. Okay. But you want this delta V to be large. You want sense margin to be large. Because in the circuit, there will be some noise, right? In practice, you have noise in the circuit. So if the noise is higher than this delta V, then you cannot deterministically read out. So you may read out the noise. So you want this delta V to be large enough, to be larger than any noise in the circuit. So you can safely and reliably read out the information. So you want this delta V to be large. If you want to have delta V large, from this equation you can see that CBL and CS, which one to be larger? So this is in denominator. So if CBL is smaller than CS, CBL over CS will be small, and 1 over a small term will give you a large value. So then you want the CBL smaller than CS. And typically today, like the CS is like 20 femtofarad for the typical DRAM. A CBL you want less than that, maybe 10 femto, 5 femto, you want less than that. So you can get some reasonable delta V for the sensing. So any questions on this slide? Okay, no questions, then we can move on. So we want to discuss the write-back process in the DRAM. So what does this mean? So here you see that we have this charge sharing process. So the voltage on the DRAM cell, its SN node, is decreasing over time. But we don't want to change the data when we read out the data. We want to have the same data even after we read out. So that means we have to restore this voltage back to VDD because this SN, this orange line, this is the voltage of the storage node. We want this storage node to be VDD again after we read out because we don't want to change the data when we read. So how do we do that? So here we need to consider this write-back process, how to recover this SN voltage. Because at this moment, due to the charge sharing, we develop the delta V on the bit line, but at the same time, the storage node voltage is kind of decayed. So we want to bring it back. So the trick to bring it back is to use the sense amplifier to do this job. So let me briefly introduce how to amplify the signal. We have that delta V. How do we amplify that small signal to a large signal? So here we can have this DRAM cell. Let's say still is 1T1C. So this is your storage node. And this is your bit line. So this bit line will be, of course, you have many cells attached to the bit line. But at the end of the bit line, we will have so-called sense amplifier. So here, this blue box is this sense amplifier. This is to sense the small voltage difference. And sense amplifier is a differential amplifier. It's like your op amp. You need to have differential inputs. So here, one input is through this bit line, and the other input is through a reference line, or sometimes we call it bit line bar. But let's make it clear. Here, we call it a reference line. Reference line. So this reference line will be always kept at half VDD. So it's a reference. So it's a constant voltage, half VDD. But the bit line here, as we discussed, if you store 1, you will develop this half VDD plus delta V. So here we're going to have this sense amplifier to detect the difference between this half VDD and half VDD plus delta V. This sense amp is based on a cross-coupled latch. It's similar as SRAM we discussed before. You see here Q1, Q2, Q3, Q4, 2 inverter cross-coupled. So it's a latch. But this latch is not the same as before because to the ground here is connected with a NMOS transistor Q5, and up here to the VDD, it connects through a PMOS transistor Q6, and this Q5 and Q6 are controlled by the clock 5S. So here, the magic here is at this moment, we are going to turn on this bias. So the sense amplifier activates signal is to activate this bias. This is because before the bias is activated, this Q5 NMOS is off. This PMOS Q6 is also off. So this latch is a floating circuit. It does not have ground or VDD, so it's floating. Those floating circuits, you know, the voltage can be arbitrary. These two loads can be any voltage, so it doesn't matter. But so it doesn't matter. Okay, this two load voltage doesn't matter. So this two load voltage will be determined by the outside because it's floating. Okay, it's not determined by the Q5 or Q6 internal circuit. It's determined by external because it's floating. So this load will be determined by the half VDD here from the reference NAND, and this other load will be determined by here half VDD plus delta V from the bit NAND. But at this moment, okay, the bias is turned on. So bias is turned on, then this circuit is going to work because you have the ground and the VDD. So it's a latch. It must flip, okay, because latch only have two stable points, and in this case, because the right-hand side is larger, the voltage, so this node will be flipped to 1. The other node will be flipped to 0. This is simply because it's a latch. And in this waveform, this beta bar is a reference NAND. This is a reference NAND. So after you turn on this bias here, so those two loads is going to flip. And then this one, the bit line will be flipped to 1. That means it's going to be VDD. And the other side is going to discharge to ground. So you see the BL and BO bar, or this reference line, is going to split between 1 and 0. So this node becomes 1. That means the bit line is becoming 1. So this 1 will be propagate back here. This VDD. Now this will be charged up to be VDD. So this VDD is going to write back the data to be the SN node, because SN node at this moment is already decayed to this value. Here is lower than VDD. Now the BL is becoming VDD, so this VDD is going to charge back this storage node. So the storage node will also increase to VDD. So you see here in this waveform, in the write back process, first the BL is flipping up to the VDD, and the SN, which is orange line, will follow because it's also charged up to the VDD. And eventually, both of them will reach VDD. So the write back process is complete. And after that, you can turn off the word line. The read operation is done. So you already read out the data, and then the data is restored. So the process is done. Any questions here? So I know it's a little bit tricky, so you can review the video after class. If no question, we can stop this clip.